Let me start. I think I have time. Let me start from the beginning again. Do you mind? Or so I will be talking about using excimer laser to manufacture stimulative and stimuli responsive membranes. 248 nanometer krypton fluoride excimer laser can be used to manufacture temperature and pH or stimuli responsive polymer-based membranes for controlled transport applications. This is done by a two-step approach. In the first step, well-defined or shaped and orderly pores are created on commercially available polymer films by ablation using excimer laser. The same laser is used subsequently for energetic grafting and polymerization of a responsive hydrogel polymer using pulsed laser polymerization, or PLP, inside these pores. This is a fast process which offers flexible tuning of flux using laser operation parameters. Membranes with 600 nanometers to 25 micron pore sizes can be fabricated using the laser through different metal mesh templates. The size of the pores generated by laser ablation can be reduced down to the nanoscale, less than 100 nanometers, for flux in the film plane by using self-assembly technique. Polymer films processed in this manner can be stacked on top of each other and can even be incorporated with responsive hydrogels by PLP within the channels created on their surfaces. Experimental results show that membrane manufactured by excimer laser are excellent choices for applications where transport or transition uniformity are the prime requirements, as they possess uniform pore sizes and distributions. So let me talk about the motivation for the work. The motivation is really in terms of comparison with other techniques. The first one is phase inversion, which uses precipitation from vapor phase or controlled evaporation. And thermal precipitation and immersion precipitation are also used. Solvent exchange and precipitation of a polymer is followed by the evaporation of a non-solvent and pore formation. On the upper right here, we see an example for phase-inverted polyethylene sulfone membrane. Interfacial polymerization involves polymerization of a reactive monomer at the interface of two immiscible solvents. Electrospinning involves non-woven fabrication technique using a high-voltage power source with a syringe pump, a ground collector, and a spinneret to spin a polymer solution into a non-woven fabric form. Membranes with pore sizes varying from 10 nanometer to several micron can be produced in this manner. On the lower right, we see an example of polyvinylidene fluoride cohexylfluoropropylene electrospun membrane as an example. Stretching involves hot stretching of an extruded semicrystalline polymer film, which acquires pores by lamellar separation. On the right, we are seeing a polypropylene polyethylene membrane prepared by stretching. These typically result in non-uniform distribution of pore areas due to the nature of semicrystalline structures. Track etching involves irradiating a polymer film using high energy from fission or the use of ion beams to create tracks on the film. Pores are subsequently created and widened using chemicals. On the right, we see two examples. One is polyethylene terephthalate, and then polycarbonate on the extreme right. In this technique, pore overlapping typically results. All of these methods result in non-uniform pore size, thus increasing tortuosity of the solute transport, making it difficult to predict the transport rate. And all but the stretching involve the use of environmentally undesirable solvents. Now, what is the alternative? We are offering the use of excimer laser by using 248 nanometer krypton fluoride laser. We have used them, for example, on polyethylene terephthalate films of thickness 72 to 124 micron, over which different opening sizes, in this one particular case, from 30 to 43 micron, stainless steel mesh masks were placed to manufacture different size perforated patterns and provide an effective and controllable perforation technology. Now, we also illustrated the manufacture of densely packed polystyrene and silicon nanodots using top-down, bottom-up hybrid method by excimer laser irradiation on perpendicular cylinder-containing black copolymer films as masks. Black copolymer self-assembly process was employed, first providing upright PS nanocylinders in polyisoprene or PI by the control of segregation forces between the PS and PI block domains. Preferential ablation of more UV-sensitive block components, which is PI, along with the non-selective removal of all block components, reduced the overlap sample thickness. The upright PS nanopatterns were transferred to the silicon substrate with ablation of PI and creation of nanodots on silicon simultaneously at an appropriate laser intensity by matrix-assisted photothermal ablation in the less UV-sensitive block component PS. Here's an example of this application of this method. So here we are using 130 millijoule per square centimeter fluence excimer laser on the surfaces of 100 nanometer thick black copolymer, styrene, isoprene styrene, mixed with the homopolymer of polystyrene with different molecular weights, 12,000 and 15,000. The thin black copolymer mask could be completely removed after 100 pulses. Thus, the size of the membrane pores generated by excimer laser ablation can be reduced down to the nanoscale for flux in directions transferred to the film, in other words, in the film plane, using this innovative self-assembly technique. Polymer films processed in this manner can be stacked on top of each other and can even be incorporated with responsive hydrogels by PLP within the channels created on their surfaces. This is preferably done prior to stacking. And they can be used as membranes with flux in their planar direction. Now, let me talk a little bit about stimulative membranes. We used ablative procedures, which we developed earlier, on a variety of polymers, which are summarized here: PHB, PLA, PMMA, PU, PDMS, by using the same laser at 248 nanometer to produce cavities and orderly perforated holes on them for tissue engineering by examining cell polymer film interfacial interactions based on the proliferation of human fibroblast cells cultured on the laser-modified membranes in comparison to unexposed membranes and tissue culture dishes as controls. Among these, the biodegradable PLA, polylactic acid, and polymethyl methacrylate, PMMA films, revealed that the presence of laser-induced perforations spurred cell proliferation on and around these membranes, while the presence of cavities without complete perforation did not have any effect on cell proliferation. Obviously, the presence of perforations of certain sizes is a unique factor in increasing cell proliferation, and these therefore can be used as effective scaffold material for tissue engineering. Now, the method that I mentioned to you at the beginning, as I indicated, has two steps. In the first step, we have the ablation of the polymer film by pulse laser through a mask, and the perforated holes are created. These are typically in more or less a conical shape in the cross section. And these films then are subsequently immersed in grafting solution, which is a hydrogel, which induces the stimulative or stimulative component to the membrane. The ablation process itself is well known. It is mostly by photochemical ablation, and in many cases, however, photothermal ablation can also accompany this process. As we know, photochemical ablation, the absorption of the UV photons excite the electrons in the material to an excited state, and the composition in the material occurs. With the photothermal ablation, an additional step is involved, whereby internal conversion through this path 2 is occurring to a vibrationally excited ground state decomposition. This process is governed, as long known, by the Beer's law, as shown here. Here, D is the etched depth, which we usually are interested in. And as you can see, it's a function of the absorption coefficient of the polymer material. It's also a function of the incident fluence and the material's ablation threshold. By using this method, we are able to create well-ordered and very well-defined, clean perforations. You can see in this case, we are using a square mesh. So even the edges, corners are all well defined. Now, what is the system made of? First of all, of course, we have the excimer laser, krypton fluoride at 248 nanometer. In this section, we are careful to minimize the photothermal effect, as I mentioned earlier, because photothermal components will disturb the membrane around the perforations. And also, with respect to the PLP, in the grafting step, we don't want the hydrogel material to be affected and damaged or degraded. So these are the two aspects that we have to be careful about. For the base membrane, we have a whole slew of polymers, as I listed here. And so the options are quite wide. For grafting material, if you want thermoresponsiveness, we can use polyisopropyl acrylamide or P-NIPAM hydrogel. This material has a lower critical solution temperature, LCST, of 32 degrees centigrade. This is very close to the human physiological temperature, and as such offers potential for biological and medical applications. Polyacrylic acid, on the other hand, PAAC, can be immobilized with glucose oxidase to detect the presence of glucose and respond corresponding to amount of glucose present in the system. So this can be used for medical applications in conjunction with diabetes. The ablation process I described already. We have the krypton laser. In this case, we are bending it with this mirror and going through this lens to adjust the focal length. We have the gate of desired dimensions, and then it goes through our mesh, whatever lithography you want to impose, and then impinges on the polymer film. Now, the photothermal effect, of course, there is ablation products coming in. We use a vacuum pump to evacuate these byproducts. but in any event, we still have some affecting the surface. So the surface of the membrane film most often will need to be cleaned, but it can simply be cleaned by using DI water, for example. In more severe cases, you may want to use THF, etc., some other chemicals. Here is a video of the process. You can see in progress here, the pulse impinging on the activity. So what are the advantages? We have a process that is less time consuming. It's organic solvent free, unless if at the very end, if you have to use some solvent, but this can be avoided in most cases. Uniform pore size is obtained, along with narrow pore size distribution. Here we are looking into a variety of geometries that we produced. On these frames here, we see the process conditions. Small d is the thickness of the film, in this case varying from 50 micron to 125. M is the mesh opening size. Cap F is the fluence of the laser. Cap P is the number of pulses. And small f is the frequency of the laser. Our laser, of course, can go up to 400 hertz. So you're able to, if you're able to match your process, you can do this very, very quickly. Here's a table that maps the mesh opening to the actual mesh opening in microns to the mesh grading. We can see on this table, on this graph, an experiment that shows the effect of fluence on the average pore size that is obtained. You can see in these. These are for different film thicknesses. You can see 50 to 125 micron. And the average pore size is obviously increasing with an increase in fluence. Now, the experiments show that increasing the mesh opening size results in larger average pore size, cleaner edges, more uniform shape, well-defined pores, and smaller affected area, which are indicated by these dark areas. For the PLP, we are immersing the ablated film in a closed and isolated grafting solution, which is the responsive part. But the rest of them is quite similar to the ablation technique. That's why it's a very quick and efficient method. This is done under a nitrogen environment. Now, the PLP is a radical polymerization technique. With each pulse, new radicals are formed and propagate in the monomer solution. During the dark time between subsequent pulses, chain propagation on live radicals continues, while overall concentration, radical concentration, decreases due to the radical termination. And the material is thermally responsive. So we have either a lower critical or upper critical solution temperature. Here I'm referring to the lower critical solution temperature you can see here. So the important physical phenomenon occurring here is the transition from below the LCST to above the LCST. Below the LCST, we have the polymer is in a swollen state, you can see. Above it, it shrinks, it deswells, and what happens is that this opens the pores, so the permeation increases. So going back to the PLP process, as we are polymerizing, grafting is taking place, and that is the process as the polymerization proceeds. So the characteristic chain length is increasing in this polymerization process, as given by this equation here. As we increase the number of pulses, the degree of grafting and cross-linking of the hydrogel increases. So what happens is that this will give us a smaller and smaller paths for the solute to go through, to permeate. And this is again due to this swelling and deswelling process. These channels are created through this swelling and deswelling process, going through the either LCSD or UCSD, which will be the mirror image of the LCSD in some certain hydrogels where you're going in the other direction. So the PLP is therefore progressing. We are grafting the polymer, the hydrogel, onto the walls of the perforation, and this swelling below the LCSD. In this case, remember I mentioned P-NIPAM is 32 degrees LCSD, and then deswelling above is occurring, and this is really due to the interaction with the water in this particular experiment. P-NIPAM interacting with the water, and certain hydrogen bonding is occurring as depicted here. So the idea is, as we swell the material and control the pore sizes, we go towards a single file diffusion. Okay. You can also control this depending on what molecules. Here, I'm just simply talking about water, but we have also done experiments with caffeine, for example, and in real life, you may be doing this with a variety of chemicals. But you want a controlled diffusion taking place or transport taking place through your pores. The process itself, as I mentioned, is very well controlled. You can see very clean, well-defined pores, well distributed, and which occurs, the whole process occurring over a very short time, as you can see here, in a matter of seconds, in 2 digits, 12 to 36 seconds. These are the grafting conditions. Now, the grafting, of course, will be affected by the molecular weight of the monomer and the cross-linking agent, as well as we have a photo initiator. So the strength of the photo initiator will also have an effect. So these are additional conditions in addition to the laser. Like here, we are using 25 frequency of 25 hertz. We can also use the graphing conditions as additional control parameters. Now, we have done experiments in a permeation cell, in a filtration cell, which is shown on the left here. And by making, this is just for water permeation, we have measured the permeability coefficient, which could be calculated. And we have also normalized this with respect to the possible viscosity changes with temperature, as well as the size of the perforated holes. Here we are looking at the results, experimental results. On the left, we are below the LCST, and on the right, we are above. We are on this section chart here. We are above on this side, which is deswollen. So first of all, we note that the top curves are for the case where there's no hydrogel grafted, so the permeability is high, right? And then we graft the hydrogel. This is at different pulse numbers. So as I remember, as you increase the pulse, the permeability will go down. So, and also as we increase the thickness, again, the permeability is going down. But these are below the LCST, okay? And then we go to 43 degrees centigrade, which is above the LCST, and you can see this whole family of curves have shifted up. So the permeability, permeation coefficient have increased, okay, above the LCST. So we have this stimuli temperature responsiveness clearly seen, okay, through this experiment. So in conclusion, we have shown that we can use 248 nanometer krypton fluoride laser for both stimuli and stimulative membranes. Again, remember stimuli, we have mentioned temperature and pH for the pH for more like glucose diabetes applications. And for stimulative, we talked about the tissue engineering. In the stimuli responsive part, we use the two-step approach. The first step being the ablative part, and the second part being the PLP, pulse laser polymerization part. And so we could control these processes by tuning the laser parameters as well as this grafting solution parameters. So we illustrated how that can be done. So the results show that the membranes manufactured by excimer laser are excellent choices for applications where transport, transition uniformity are the prime requirements, as they possess uniform pore sizes and distributions. And I also mentioned that we can reduce the pore sizes by using the innovative self-assembly technique by black copolymer self-assembly. So that's also possible as another process. And finally, the stimulative membrane application, important in medical applications for like tissue engineering as scaffold materials. With that, I would like to close and thank you very much for your attention.